of having some errors in multiple bits is really very less if we apply source code, which is kind of an improvement. And post that, we have seen that the concept of bit flip error as well as the phase flip error, and how Shor's algorithm is able to cater both the kind of errors, both the bit flip as well as the phase flip. And then we entered into the primary discussion of the cryptographic context. So we have seen that classical cryptography, what are the different variants of classical cryptography, where we have seen there is a concept of symmetric key cryptography or the shared key cryptography, as well as for the asymmetric key cryptography or the public key cryptography. And why the key, what is key and why it is very important, what is the key size, that is very important in this context, and how the key size offers different security levels, or how we can alter our security levels offered by each of these cryptographic algorithm depending on the making the changes in the sizes of the key. All these things we have seen, their real impact also, why it is exponential, all those things we have discussed. Okay, and we also have seen that how many keys are required, why it's called an asymmetric key or the public key. So part of it is public, a part of it is private, and the part which is public is used for encryption, the part which is private for use for decryption. And for each of the user, we need a pair of the public and a private key. So for n users, we need at the maximum cases 2 into n number of keys total. Okay, that is n number of public key total plus n number of private key. So 2 into n number of total number of keys. As well as for shared key, we have seen that in the worst case, if there are n number of users who are interacting somewhere in some fashion. So considering in the worst case, they can have how many number of interactions that can take place simultaneously. Depending on that, we have to choose the number of keys. So maximum number of interactions in an undirected graph with n nodes can be n into n minus 1 by 2, which is nc2. So similar formula here also applied. If each edge we can actually think of to be equivalent of the key. Okay, one key, one shared key. So one edge is equivalent to one key, considering that it was nc2, which is n into n minus 1 by 2. Followed by that, we have seen that a few of these like quantum algorithms, which are like Shor's and Grover's, they are causing real threat to all these existing cryptographic techniques. Where, just to give you a quick recap, we have discussed that the asymmetric key encryption algorithms, like say RSA, elliptic curve, digital signature algorithms, all these algorithms, they are actually broken or thought to be broken in near term by Shor's. That is, their inherent mathematics relies on integer factorization or discrete logarithm technique, which is broken by Shor. And for symmetric, it is not kind of a broken. So symmetric or shared one is not as in a threat position as our asymmetric ones, but definitely they are also under threat because of another algorithm called the Grover's algorithm. And so we concluded here that a Grover's algorithm is actually not breaking maybe, but it is definitely weakening the existing symmetric key crypto system. And in what order? In exactly in a quadratic fashion. So if it was like a 2 to the power 128 for a AES 128 encryption, right now through quantum, through Grover, it will be now 2 to the power 64. So for brute force as an eavesdropper, I need to now perform only 2 to the power 64 number of combinations instead of earlier, or in a current situation, I have to apply all the 2 to the power 128 number of comparisons or say attack scenarios I have to design for AES. So this is the power that quantum is offering, and this is the threat that quantum is bringing. Let's not call it public key and private key, because it's not about key, it's about the encryption system itself. So let us call it is a causing threat to both public key crypto system as well as private key or say shared key. To be very specific, it's not called a private key, it's called a shared key or symmetric key crypto system. Only the difference is that it is more threatening to the public key a little bit less threatening for the symmetric key, but it is definitely causing threat to both the cases. The first one is caused by Shor's and the second one is caused by Grover. Okay, so on that note, on that kind of a concept in our head, let us just start today's discussion. So now we have understand that, okay, something needs to be done. The existing system is really not that much of a reliable as it was so like for these many years. Right now we have to think of some solution. हम चुप नहीं बैठ सकते. So on that note, researchers started exploring it. They explored something, that is, two types of solutions are possible. One is that either we can have, because if we very carefully notice that why public key is under threat because of SHOR. Because public key crypto systems are based on integer factorization. Listen very, very carefully. Because the public key crypto systems rely on the integer factorization or the discrete logarithm problems. Now, if I, instead of using these two algorithms, if I rely on some other techniques, which is based on some other mathematics, which is very difficult, even some way difficult to be performed by also a quantum computer, then can I tell that they are not as vulnerable as what we have right now? We can of course say that. Because if in any way we cannot develop a quantum logic, or the logic development is not that easy as that of a like a integer factorization or discrete log, then we at least can say that, okay, now this is for quantum also it is a bit hard. So it is not the existing crypto system. So this kind of thought process brings into picture a different era of cryptographic computing, which is known as post-quantum cryptography or PQC, which also is known as quantum resistant cryptography, alternatively known as quantum safe cryptography. So all of them mean the same thing. Post-quantum cryptography, quantum resistant cryptography, quantum resilient cryptography, quantum safe cryptography, all of them mean the same thing. Where we believe that, okay, so instead of using the same mathematical functions which we are using so far for encryption and decryption, let us use some other kind of algorithm, which is a bit more inherently mathematically hard. So it is not that they are never breakable. So there is no information theoretic security around PQC or post-quantum cryptographic techniques. But it is definitely guaranteeing that it is not as vulnerable as we have in our existing asymmetric key encryption. This is called post-quantum cryptography. Now, the major point that you should be taking care of here is that it is based on absolutely a classical technique. So post-quantum cryptography has nothing to do with quantum. Okay, so post-quantum cryptography is not at all equivalent to or equal to quantum cryptography. It is completely different. It has nothing to do with the quantum. It's just that it relies on classical technique, but the classical technique that is right now is relying on is completely different than the existing techniques that it used to rely on. That is the thing. And why we call it post-quantum? Because it is kind of a practices that we want to adopt or adhere to its standards depending on once we have a quantum computers available. So it's a post-quantum era. Cryptographic practices at post-quantum era is known as a post-quantum cryptography. Why it is called a quantum resistant one? Because since it is not based on the integer factorization or discrete log, we believe that this will be at least resistant to the quantum threats because of Shor's and Grovers. And for similar reasons, it is also called a quantum safe cryptography, not just for the same reasons. Okay, so PQC or quantum resistant cryptography, that is basically when your traditional cryptographic scheme, just look into the slides now. So the traditional cryptographic schemes deployable on classical computers and known to be quantum resistant. So it all has to do with the classical thing, nothing quantum. It assures a mathematical hardness when compared to the existing public key crypto system. With respect to the existing system, it is more mathematically hard. Okay. Third one is It provides a security against quantum attacks and impacts of Grover's as well as Shor's algorithm. Because Grover and Shor, none of them can work if we do not employ any of the discrete log or the integer factorization thing. So maybe I am very powerful, but if I do not know how, say for example, a table is built upon. So obviously, like my knowledge or my expertise will have no kind of influence on the table, say manufacturing. So similarly, table manufacturing is kind of a PQC. If I am a quantum computer, no matter how hard I am, if I do not know the logic, how to break it, how to break the manufacturing process of a table, I'll be unable to do that. The process of the recipe is unknown to me. Similar to the, like the same concept is here also being applied. Second one is, alternatively, depends. Yes, a very good question. That can later on we can claim that PQC can be broken. We do not know. The answer is we do not know, but definitely there is a chance. So the what we can currently conclude or comment on is, it is not guaranteed. It is definitely not theoretically secure against a quantum threat that can occur in any future, maybe near term future, or say 30 years after, 40 years after. If we do not know that, because we do not know how the development or evolution of quantum computers or the computing principles will be taking place. So what we can currently comment on is, quantum resistant cryptography is definitely our alternative solution to the existing ones which we can currently rely on. Why we can currently rely on, I will tell you. There is a business aspect to that as well. I will be talking about that. But at least it is kind of an alternative solution that we can rely on. Kind of a कि बच्चे को जिससे आप मतलब kind of a chips or lollipop that you can give to a kid कि अभी तो you are safe, don't worry. It is not something that right now something very bad can happen to you. But definitely that does not mean if there is an enemy, then we cannot really conclude that it is never under threat. That kind of a theoretic security is not provided by PQC or quantum resistant cryptography till date. Maybe some mathematical kind of an assumptions might come, some theorem or lemma might come, but right now, till date, we do not really rely on it. So right now it's in a very kind of an experimental stage. So different kind of an algorithms are being proposed and few are being validated. Then that are on those validated algorithms, some of the testing is being done. If it is approved, then we are using it somewhere. Maybe someone is again kind of cross validating it and talking about it that okay, no, it's not really that much of a strong, it might be broken. So we are neglecting it. So that kind of theoretic security, just like I used to in the last class, I told you, I talked about it, that a quantum random number generator, which again I mentioned that today also I will be spending 5 or 6 minutes on that. So a quantum random number generator, if that is built on a quantum logic, then it is definitely inherently. Why? Because quantum systems are inherently run. So on that note, the quantum random number generator built on or based on the logic of a quantum source of randomness will also be inherently random, which is never true. For example, in case of a pseudo random number generator, which is generated using some of the, just ask the questions later, maybe then it will not break the flow. Some of the like a pseudo random number generator, which are based on some high periodic functions, and we are using it for cryptography. And also there is another kind of a random number generator, which is known as a hardware-based random number generator. For example, the sea wave or wave noise, or say the road noise, environmental, anything related to the natural process, environmental process, we are actually using in order to determine the randomness or entropy. Entropy means the measure of randomness. So the more the entropy of my system is, the more random my system is. The less the entropy, the less randomness. Okay, so it is not the case. Okay, so hardware random number generator are based on the wave noise or atmospheric noise in some way or the other. Okay, but still that we believe that they are also not very much of an inherently random, though they are not built on some a mathematical process, but still it's a macroscope. So maybe I am able to do a certain manipulation on the outcome. I do not know. Maybe I'm able to do some manipulation. So that is why we call that hardware random number generators or HRNGs. They're definitely more secure than the pseudo ones, but also definitely not as secure as your quantum ones. In an ideal scenario, considering quantum ones are not biased and they are really random and they are not noisy. That much of an idea. Okay. Noisy means here in terms of a decoherence. Not noisy does not mean in terms of a random. It is random, but it is maybe not decohering random. So based on this thing, so quantum resistant cryptography to ho gaya. This is one of the solution. Researchers are working on that. Another solution they have also thought of, which is a quantum cryptography. What is a quantum cryptography? That they have thought of that instead of using a resistant version of cryptography, if we are able to encode our data, encode our the entire like data sending process through a quantum channel, even if it's not being affected by a quantum computer, that was their kind of a focus or aim or motto. The answer is no. If you are successfully able to encode something, some of the data that you want to send through within some of the quantum register, and that quantum register through some means, within double quote some means, you are able to transfer to the recipient, then you can say that it is also a more secure solution than that of your quantum resistant system. Okay. Yes. So why? If you ask me that why we are claiming this kind of things, because the quantum source, the way it works is random. Second is, even if as an eavesdropper you have some data, you are unable to predict what that data is until and unless you check it. Now, once you check it as an eavesdropper, once you check the quantum state itself, what will happen? It will try to change its form. It will like instantly begin to decoher. And before decoherence, even if you try your level base to copy that state into some other qubit, it is not possible because of the no cloning theorem. And once you do any tampering, it will ultimately, eventually, at that very moment, it will start losing its quantum information. So for all these quantum phenomena, we claim that a quantum system is really, a quantum cryptography is really secure over the classical cryptography. But conditions applied here, it has to be a quantum channel being established. Your quantum key should be properly distributed between a sender and a receiver. And whatever data that you want to send, you can directly send it with a certain kind of a encoding to the through the channel. Once it is reached there at receiver's end, that is through the classical channel, the data has been transferred, and through the quantum channel, the key has been transferred. As a receiver, I should be able to interpret from your data as well as key and receiving both of them that what was your initial information that you wanted to send. So this process is a quantum cryptography process. Okay, and quantum cryptography is basically realizable with the help of two different technology. Uh, First technology is the quantum random number generator. The second technology is a quantum key distribution or a QKD. Both of them are based on some of the or mostly at least the hardware oriented aspects of quantum. Okay, I hope so far you do not have any doubt, at least to the introduction of PQC as well as the quantum cryptography. Is it okay? Because if I say quantum safe cryptography and if I say quantum cryptography, you should be able to differentiate between both of them. They are not the same. Okay. And for the rest, is it okay? Definitely. Definitely there is a pictorial representation. Just wait. That is for the quantum key distribution. Definitely. Okay. So post-quantum cryptographic schemes, they are mostly like categorized into all these things. So hash-based, code-based, multivariate based, also say for not. I'll be talking about it, Dipshika. I'll be talking. Just give me some minutes. Then lattice-based and isogenes. Okay. And these are all the techniques used for this. Since there is another session for QT02 as well for this PQC, so we will not go into much of the detailed techniques for it, which we will be covering maybe in the next QT02. But it is just that I want to tell you that what are the real things that is happening here. So just remember that out of all these techniques, so which is the most promising technique that is based on the lattice-based cryptography. PQC. Lattice-based cryptography uses the concept of a lattice algebraic structure, which again relies on some shortest vector problem, okay, or say closest vector problem, whatever you call it. They are interchangeable, and some very few quantum algorithms for these kind of like post-quantum cryptography PQC has been developed, but mostly they are based on the lattice-based, and they are crystal Kyber, crystal dilithium, and Falcon. And last one, as according to the last say round, there are only 4 algorithms that are currently in use as per the last state. Okay, I guess 3 to 4 months back. So it was only out of the 4 algorithms, only one algorithm belong from hash-based encryption, which is Sphinx Plus. Okay, so it uses kind of a Merkle tree or that kind of a, it will be Merkle tree signature scheme, kind of a extended Merkle tree signature scheme, XMSS data structure. So kind of a tree data structure for a hashing. And all the remaining 3 algorithms are based on the lattice-based one, where the crystal Kyber, crystal dilithium, and Falcon. These 3 algorithms are approved. And out of them, only the crystal Kyber is one of the key encapsulation mechanism or KEM algorithm. Okay. And crystal Kyber, the KEM algorithm means it is used for encryption and decryption purpose. And all the other algorithms, that is a Falcon as well as a crystal dilithium, all of these are for the digital signature. As well as Sphinx, which is a hash based. So all the remaining 3 approved ones are for digital signature. Only KEM algorithm, I don't have that knowledge. Thank you for sharing. Maybe. So what it was based on? What kind of technique? Lattice based again? Okay, it's based on codes. Thank you. So far, we have to wait. We have to wait. Maybe it is approved, but just after approval, a lot of algorithms for from isogenes and code based, all of them were discarded by some researchers. So even if something is approved, maybe in the later round, we have to wait for one more round just to check that if someone tries to like cancel it out or not in that way. Definitely. Okay. Thank you for sharing this. Thank you for sharing. So accordingly, so these are like in a very like niche level. So a lot of algorithms are being developed. A lot of algorithms are being sent to NIST. Okay. Then due to some reason, they are trying it out for respect to some powerful classical computer. They are trying to break it with a classical computer. If they're able to break it, they are claiming that, okay, no, this is not really quantum safe. So likewise, they're discarding it. Okay. But I will definitely refer that for your interest, or even later we will be discussing more on these schemes. I'll be definitely talking about it. I again had mentioned that this is a topic that is there in the QT02. Just hold on for some minute. I'll be discussing about, if I get a chance to discuss, or someone else will be discussing about the Kyber, dilithium, all these kind of schemes in a bit detailed way. Just hold on for some maybe days. Meanwhile, if you want, you can go through it. But definitely for your interest, So all these things, but one thing that you should be keeping in mind is all the 5 techniques that they have discovered, all the categories, they are really different from the integer factorization and the at least have the idea, because QT01 is all about the fundamentals of it. And though we discussed a lot of on the quantum algorithm part. So all these 5 techniques are based on the different models of mathematical functions. Okay, which is not the same as that of the existing ones. But there are definitely like all these schemes. So every advantage comes with some sort of disadvantage. So the disadvantage that is there with all the algorithms are, so right now we directly, if we implement something, we cannot directly like use it. So that kind of a barrier is there. And why? Because though they are here, but they are computationally, they will be so much of an intensive. So they will incorporate so many number of resources, and that will be so time consuming. Or the operations itself are so complex that we often actually ignore it. Okay, so the main challenge is to reduce the key size so that it is really implementable, to have a easier ciphertext which we can actually send. So all these things, to reduce the number of iterations, all these practical challenges are occurring into picture because of the mathematics that is being encoded here. That is so hard and so much of a not in a quantum friendly structure, so that is very difficult, even in a classical friendly structure, because there are so many number of trapdoor functions here, so that is becoming a bit difficult. But definitely the all these things are taken care of. So what I believe is maybe not directly, again it is my only my intuition, that is maybe not directly entirely PQC, not maybe entirely like most or say quantum cryptography. So what we want to have, or that is a beneficial thing for us, is to have a hybrid of all the 3 things. So classical ones as well, and then PQC one, maybe either this combination or PQC plus quantum cryptography. This combination plus 3 is PQC, cryptography, quantum cryptography, as well as the classical cryptography. So somewhere around this kind of concepts might ask. But none of them are really under threat because of Shor's and Grover's algorithm. Okay. So post-quantum asymmetric crypto algorithms, that is quantum resistant schemes without factorization and discrete logarithms. So this is basically the quantum resistant schemes which are not using any factorization or discrete log. So they are mostly based on the learning with errors based on the lattice problem. We will be discussing about this PQC in a detailed way. This is just for the introduction to PQC. And so this is serving as a basis for a variety of public key and a signature scheme structure. And ring learning with errors. So ring LWE, this is another kind of advanced form of lattice based one. So which used an additional structure that allows us for smaller key sizes. Multivariate, here we use a kind of a non-linear, usually quadratic polynomial over a finite field. For code-based, some error-correcting code kind of concept are being used. For hash-based, I just said that XMSS or extended Merkle signature scheme, that kind of a data structure is used based on the hashing scheme. And super singular, it is basically some sort of finding isogenes between the super singular elliptic curve. Okay. A motivation between quantum resistant cryptography is hash-based algorithm and encryption algorithms are under quantum threat in post-quantum era. So SHA, hash algorithm, current security level is 256 as it is SHS 256. Post-quantum security level is 128, and how this is happening because of Grover. Just check the first two. Second one, similarly, it's 256, 128 in the post-quantum level, it is Grover 4. Followed by this, all these things where you will be having an effect of a shared key. Now, this is for the asymmetric key where ECDSA, elliptic curve digital signature algorithm, RSA. Okay, the last two are not asymmetric, the last two are symmetric, AES 128 and 256. So it's kind of a mix up. Please Keep it in mind. So only the first four are based on the asymmetric ones. So all these are having some security level 128, 80, 112, 128. So after like till a certain level, it is basically zero. That is, it is broken because their post-quantum security level is in terms of 0 bits because entirely it can be broken. And how that kind of a broken thing is taking into picture because of the Shor's algorithm. Okay, and AES to 128 and 256, they are kind of a secure as they are using Grover, and it is kind of a weakening it, not really breaking it. Okay. So now there are several post-quantum initiatives. For example, the first one is this like all these things like PQ crypto. The second one is weakening and broken. Ritash, yes. Ritash, I explained it. Like weakening means just if you notice the last class, we were talking about this thing that Shor's algorithm basically is breaking it. Maybe that means that it is already able to entirely break the crypto system. But Grover, what it is doing it, whatever initially, say for example, just consider the last two rows, initially AS 128 and 256. So AS 128, it is actually giving me a search space of 2 to the power 128. But for Grover, okay, meanwhile, say for example, now I am an intruder or eavesdropper. So I want to perform the, or if you want to calculate the AES key, then I'll be doing what? I'll be doing some sort of cryptanalytic attack. Maybe I'm applying a brute force attack. So I'll be doing a brute force attack on all the to the power of 128 number of combinations. So to the power of 128 is my success. When comparing this, I have to find the perfect kind of a pair or match for which I'm getting my solution. That is the purpose of intrusion and all. So once that is being done, Grover actually is breaking it. They faster the key search. They faster the key search in case of a whenever it is like kind of under threat due to Grover. But for sure, it is definitely broken. Broken means it is algorithmically broken, and for Grover, it is algorithmically weakening. It is not exactly broken. There is no algorithm which can exactly give you the key pair, just like in case of Shor. So where you exactly get the key pair, we call it a broken scheme. And where you do not get that one, but say I have to travel to 100 of cities in order to get one of my lost item. Now, right now I have to travel to 50 cities. So definitely in terms of the computation, there will be a huge kind of an advancement. So that is what is being offered by Grover. Okay. So, the PQ crypto, safe crypto, crypto math, PREST, and post quantum standardization initiative. All these things are some of the post quantum initiatives that is being taking place. Post quantum initiatives means what? Means some initiatives we might be required for quantum so that they are built in a way or designed in a way that it is not really under much threat because of the evolution of near-term quantum computers. That is called the post-quantum initiatives. Okay. So PQ Crypto, it is a design a portfolio of post-quantum public crypto systems. So every such agency or say whatever it is, they have certain agenda. They have some specific areas to work on. So their goal is improved speed, enhanced security, and adaptability to several performance challenges of IoT, cloud, and mobile devices. Safe Crypto, it is a secure architecture of future emerging cryptography. Underlying PQC algorithm is lattice based. Okay. Motivation is providing a robust, physically secure solutions for future IoT applications in the quantum era. Goal is to improve the security of digital signatures, authentication schemes, key encryption, attribute-based encryption, and identity-based encryption. So all these are goals of safe crypto. It is designed to achieve a 10x speedup in throughput for all real applications, as well as 5x reduction 5x reduction in energy consumption for low power and embedded mobile applications. So CryptoMath Quest is another initiative such another initiative taken by Japan Science and Technology Agency. Its aim is also to study the mathematical problems and their variations underlying security modeling, and that is the classical crypto system. So four key research areas of 25 mathematician and post doctorate 4 are so investigation of security model in industry applications, evaluation of security and efficiency in post-quantum cryptography, study on mathematical object and reduction map used in cryptography adversary, and exploration of theoretical knowledge for quantum technology and quantum information theory. So likewise, there are other such initiatives. Okay. So these are the key research areas. What kind of a cryptographic practice or PQC practice that this group is performing. And the last one is what is being adopted by NIST or Post-Quantum Standardization Initiative. So you can see the timeline where I guess the timeline almost is over. So again, the round 4 is being done. So today, whatever the one who has mentioned, maybe round 5 result or something with round 4. Some of the algorithms that have been approved today for HQC, I just got to know from one of you. So maybe likewise, there are several rounds of these kind of like submitting the solutions, just like our paper solution, paper submission. So few of them are submitting their solutions that is tested over different scenarios and that is being either approved or some way so these are the things that are taking place. So all these things are initiatives that are taking place in the NIST era on PQC. Okay. The last one, post-quantum standardization, is done by NIST, National Institute of Standards and Testing. So introduction to quantum cryptography means it is a science of exploiting the quantum mechanical properties to perform cryptography. So right now, so far we have seen at least the introduction to, we have understood the quantum states. We have also understood that we have to find a solution. Two types of solutions are possible. First type is a quantum safe cryptography, which is sort of a quantum resistant or resilient cryptography, which is purely classical. Another solution can be to think of some quantum cryptography where it is basically some sort of a quantum things that we are incorporating into the solution, right? And for that, there are certain technologies that are existing for quantum cryptography, which we will be discussing a bit about today. So science of exploiting the quantum mechanical properties to perform cryptography, it is called a quantum cryptography. Okay, because we will be exploiting the quantum mechanical properties in order to do that. Second is the best known example of quantum cryptography is quantum key distribution. Another one is a quantum random number generation, QRNG and QKD. So QKD offers information theoretically secure solution. Focus on this thing. It is an information theoretically secure solution to your existing key exchange problem. So initially, just I want to highlight a bit more. Initially, what is the significance of the third point is in classical, what is the key exchange algorithm that we mostly use? Just put it on chat. What is the most promising or the most well-known key exchange algorithm that we use in classical setting? Yes. Yes. Diffie-Hellman or Diffie-Hellman, whatever it is. So Diffie-Hellman algorithm is basically where kind of there is say in between A and B, some sort of information will be and some shared information will also be there based on the say the modulus. Now based on that, A will be generating its own key and B will be generating its own key. Then it will be shared between from A to B and B to A. on having those two things, both A and B, like A on having that information or key from B and B on having that information or key from A, will generate finally a shared key. Okay, which both of them right now have, and they will use that one in order to perform a key distribution, secure key distribution, where some other person should not be able to get that information. Okay, and on that note, there are a few other points also, that is all those things we have to take care of. That is integrity of data. That is what data I want to send to you. There, that is not corrupted during transmission. So that is data integrity, followed by privacy. That is whatever I want to share to you, that should not be understandable by any of the third party or anyone except the intended recipient. The third one is a non-repudiation, where we believe that no denial is allowed. Say, for example, if I have sent you something, later on, maybe you are denying that I have not sent that one. Or you have received something, then you also are denying that you have not received that. So that is not possible. Okay? That is the definition of non-repudiation. Yes, so all these things we have to take care of. And but the thing is that the Diffie-Hellman or Diffie-Hellman algorithm that we have now, based on the keys shared from B to A is generating a shared key, a symmetric key, which A will be using for her own purpose. And similarly, B on having the information from A and processing something on its own will be generating another symmetric key, which he will be using for communication. Okay? But if I say I am a eavesdropper, say my name is Eve, whatever say key, whatever key or information Alice will be or Alice initially wanted to send to Bobby is, meanwhile I will get a hold on that information. So I will tap that information or channel somewhere through some means, and then I will be having all the information. On having those information, I will be generating the key. Like I'll be having the key as a C or say eavesdropper. I'll be having some data from Alice. Based on that, I'll be generating my symmetric key. And instead of B, right now, I am behaving as an intended user. And I am trying to communicate with the existing say components. But even if I try to do that, will I be able to do that? No, because there is no way of not identifying the wrong, or there is no way of identifying who is the main culprit over here. Because if on behalf of Bob exactly behaves the same way to Bob, to Alice, then Alice will not be having any understanding of who is telling correct things. So both of them can be incorrect. So in that case, we actually should not rely on that this kind of that Diffie-Hellman key exchange algorithm is really that much of a quantum safe version. Rather, what solution they have thought of is we can make it a quantum key distribution instead of a Diffie-Hellman key exchange. And also because of that one, quantum key distribution QKD that is not under quantum threat, that is not under quantum threat, and it does not suffer from man in the middle attack. Okay. So now we will be discussing few more established quantum mechanical principles to be used as basis of quantum cryptography. So advantage is proven or conjectured principles impossible to be carried out using non-quantum communication. It is not possible because for a quantum channel and for quantum states, you definitely need some quantum communication channel to be there. Otherwise, it cannot work. Second one is a quantum state that is thought to be impossible to be copied. It is actually impossible or not possible in that way. We have seen it. It is called the no cloning theorem. And also third point is eavesdropping can be detected in QKD without proving knowledge to intruder. So what is the meaning of third point? It is very important. Third point means that eavesdropping can be detected in QKD, but the actual Alice or the sender will not be having any information about the intruder. How am an intruder? I can see all the quantum packets are being sent, but I cannot do anything because whatever I do, that will come in this way that it is being intercepted somewhere in between. Okay, so that means it is never allowed for me to clone into or try to copy whatever data is actually shared with a real quantum computer. Okay, but unlike this thing, QKT, this is the scenario for man in the middle attack and your kind of a like classical key exchange, whatever we say. But for quantum, definitely for QKD also, your eavesdropping needs to definitely be detected and corrected every periodically in every periodic way. Okay. So the reality of quantum entanglement is the Bell outlined three assumptions about the world, each with a corresponding mathematical statement. The first one is realism, that objects have properties that they maintain whether they're observed or not. Locality, nothing can. Okay, I'm just getting one question. Let me take it. Just a 1 minute. Let me look into the question once. Mm, when Eve detected, adding in above my question that there is nothing made, which said, uh, around the information of Eve, location of Eve, and all about. Is there any technique in quantum to know who is Eve and getting whole information about Eve when Eve attack? No. So for the last two questions of Hannah, there is no way I can say that who is my Eve, but definitely as a receiver, when say I am Bob, I am receiving something which is supposed to come from Alice. There are some certain terms or of agreements between me and Alice beforehand, and I'm getting something. Now, on getting the distorted bits, I should be able to, that is how QKT algorithms are built on. I should be able to determine that whether there was at least somewhere in between some sort of tampering or like distortion in the quantum state. Now, how logically that distortion can happen? If it has not done anything else, it should not collapse to the initial state 000 or 0 or 00, whatever you say. So that definitely means some sort of intrusion or eavesdropping has taken place. But it is not that I will be able to exactly predict that, okay, this is if and this is his. I'm not presenting the screen right now. I'm just talking about it from the chat questions. That is, there is no way that I can say that this is if. But what I can definitely detect is there is a presence of an if. So the presence of Eve is being detected here, not the Eve himself or herself. Okay. But once, and what is the benefit of that? If I'm able to predict the presence of some of the intruder while I am having this particular bit transfer, what I will do is I will actually discard it and will send a fresh one. That is it. But at least we should be able to identify it. That who can cause us threat. Identify that some, sorry, not who, that someone can cause us some threat. This thing we can identify. Okay. So locality is another point that nothing can influence something far away, such that a signal between them would need to travel faster than light. Okay. And freedom of choice, that physicists can make measurements freely and without influence from hidden variables. So nature does not follow these assumptions, which imply quantum entanglement is real and subatomic world in truly as strange as it seems like. be it whatever, be it a noise distortion or be it Eve's presence. It is not definitely something that I was supposed to get and what I am getting. So for noise thing, there are a lot of redundancy bits as well, which are added here also for QKT. Okay. So all those bits, including the noise bits that are being transferred. And keeping into mind the quantum error correction things and all everything in mind. So some of the temporary bits should be there. Some of the bits should be redundant. So considering everything, we actually send those many bits for the transfer. So we are able to identify it. That whether it is a part of the noisy bit or it is due to the like this thing, some sort of presence of some intruder in the picture. Okay. Thank you. So, introducing the quantum computing in cryptography, it's introducing the quantum computing in cryptography is by Wisner, Stephen Wisner. So, in 1960, he has suggested ideas in quantum information theory, including the quantum money, which is a building block for QKD, quantum multiplexing, the earliest example of oblivious transfer, and the superdense coding, first and most primitive example of entanglement assisted communication. So, what is your quantum money? So in quantum money, let me just show you the diagram. It is something like this. This is an example of a quantum money. Okay. So you can see there are few photons there and there is some sort of polarization of those photons, right? So based on that, we here introduce four bases. Either a vertical horizontal base, that is these two bases, or diagonal basis, diagonal plus and minus basis, which is 45-degree or plus and minus or 135-degree. Yes, someone can continuously interrupt and do that thing. In that case, we will be continuously discarding the bits. No issue. That is our purpose. If we do not do it, it will ultimately be harvest now, decrypt later kind of an attack. Your friend will be gathering all the information about your personal life or whatever it is. Now, once it is a time, maybe after 20 years, you two are doing some business or you two are into something, then at that time, he or she might try to completely have a hold on you or your process, thought process. This is the attack. This is very serious attack. Like harvest now, decrypt later attack. Okay. So we should not allow a quantum computer or a quantum developer to right now allow few of the informations from my head. Okay. So that is an intuition, that is kind of an idea. So here it is a four bases that we are using, either a vertical, horizontal or a diagonal, which is a 45-degree, or plus, that is a plus, or a minus, which is 135-degree. And each currency node, that is each node here, each node has 20 such combinations, 20 light traps. So light trap is nothing but a tiny devices that can capture and store a single photon. So if there is how much if can harm when if decrypt, that I will talk about. That depends on how much if is in sync with Alice and Bob, both of us. Okay, so her sync with both the sender and receiver. If she's that much of a lucky person, then maybe she will be able to harm more. But generally, there is a probabilistic calculation to that as well. Generally, it's not very like something that we can say that every time it has to be this much. So now for that, what is the solution? What we have to consider? We have to consider key. It might happen that for every such combinations or probabilistically a few number of combinations, Eve will be intervening. So in presence of Eve, we have to consider or you have to build our system to be as robust as that it is able to tackle or it is able to handle the situations where Eve is able to break the system or break that particular quantum state. That is my prediction and or say mine and Bob's prediction, Alice and Bob's prediction, and that of our Eve's prediction, if that is exactly same, then the chances for Eve to break the system will be more. Okay. But again, that is very rare because it is quantum. So brute force attack is not really that much of an easy task here. So each currency note contains 20 light trap tiny devices that capture and store a single photon. So since I have 4 bases, I can definitely choose for each of the light trap how many total number of possibility, 4 into 4 into 4. Likewise, it is 20, that is 4 to the power 20, which is 2 to the power 40. That is a trillion number of possibilities. Okay. And each wheel is identified with a traditional number and a database containing the polarization state. That is, somewhere I'm just writing it down in a database. That okay, this was the polarization state and this was the traditional number associated with this particular wheel. Okay. Now the concept is of polarized light and polarization. So whenever, now again, just a quick recap on quantum technologies. Uh, Quantum technologies, if you recall that when we were discussing, there was superconducting qubits, ion trap qubits, and photonics architecture. And while photonics architecture, I also, when that time when I discussed about the what are the strategic applications or areas or how to choose between for each of the use cases, that what quantum technology to rely on, there we have seen that the cryptography communication, all these things really rely on the photonics, where we behave the performance or say properties or behavior of a photon in order to determine what is the information contained in it. Okay. So whenever a light photon travels through a space, it will vibrate in a plane parallel to the direction to the photon it is traveling. Very logically, we can understand. So the angle, the plane of vibration mixed with the horizontal plane is called polarization of the photon. Okay. Now, if we place a filter called a Polaroid filter in the path of the light beam, it can be guaranteed that emerging light is made up of only those photons that have the same polarization. Why? Because others will not be able to pass through the polarizer. Okay. Definitely, then that means something which is already in sync, already in phase, will be able to perform a kind of a like we can guarantee that some sort of light beam will be passing through the filter. Okay. Now properties of polarized light. If a photon has same polarization as that of the filter, then the photon will pass through with that polarization. Definitely. Now, if the filter and the photon have polarizations which differ by 90 degrees, then the photon will not pass through the filter. And if the filter, that is a Polaroid filter, and the photon have polarization which differ by 45 degrees, and the photon has 50% probability to be blocked by the filter. So it says that if the filter and the photon have polarization which differ by 45 degrees, that is one is in a horizontal vertical basis, any one of them, and another one is in a vertical, plus minus basis, any one of them can happen. So the photon has, and in that case, 50% of probability to be blocked by the filter. Definitely, it should happen. Okay. So this is quantum money. It is why it is built because it's a fundamental concept in quantum cryptography where we have built something so that due to no cloning theorem, none of these states can be forged. So quantum cryptographic protocol to create and validate banknotes, which is impossible to forge. Okay, why? Why? Because every photon, particle, their kind of an angle, their behavior that is being sent to that is being sent to us or says for used for some storing into some of the database. Okay. So the key idea is arbitrary quantum states cannot be copied due to no cloning theorem. Hence, it is inherently quantum secure. Okay, because it is photon. Whenever you try to do anything with any of these states of photon, then it will disturb the entire architecture. Okay. So due to no cloning theorem, it is an inherently quantum secure one. Third one, a milestone towards development of QKD protocols used in quantum cryptography is relies on the same concept of quantum money. We'll see that. So quantum money scheme to prevent some sort of forfeiting is, suppose a counterfeiter wishes to make a fake $10 bill. If counterfeiter tries to put it in a random sequence of 20 polarized photons into the banknote's light traps, the density of, say the probability of guessing the correct filter sequence will be 1 by 4. Out of 4 bases, I can choose any one times into 1 by 4 into 1 by 4, likewise 1 by 4, that is taking place 20 times. Okay. Therefore, the only way to measure current or say correct polarization of photon in a light trap is to choose the correct Polaroid filter. Say if the filter in a light trap has polarization vertical, then the counterfeiter must choose vertical filter to be correct. And if, on the other hand, if the counterfeiter chooses a filter where no light will emerge, so the filter must be one of the other possibilities. So if the filter chosen by the counterfeiter is 45 degree, that is plus 45 degree or plus, or 135 degree, which is a minus, and the light makes through the counterfeiter will make a wrong guess. Okay. So thus, counterfeiter must know the current or correct orientation of the Polaroid filter to figure out a photon's orientation, but does not know which orientation to choose, as photon's polarization is also not known to us. Okay. And the difficulty in measuring a photon's polarization is, as per the physicist Heisenberg's uncertainty principle, which states that we cannot know every quantum aspect of a particular object with absolute certainty. So the difficulty in measuring a photon's polarization is, as per the physicist Heisenberg's uncertainty principle, which states that we cannot know, again focus, we cannot know every aspect, means the time as well as its position, or say momentum as its position of a particular object with absolute certainty. That is, you have to make one fixed, then you can calculate what is the change, what is everything with respect to the second one, and vice versa. You can check this one. So feasibility, what is the time now? Is it 3:30 now or what is it?
3:10, ma'am.
3:10. Okay. 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 Let me continue for 5 more minutes. Then maybe 5 minutes break I will be given. Just let me know once it is 3:50. So how feasible your quantum money is right now? It is really not very practically implementable with the current technology, as quantum states must be stored in the quantum memory. Now, what are the challenges? Quantum states, if you have to store very precisely, that is, you have to keep in mind. Now, remember, what is the main challenge? You have to keep in mind every such polarization angle, everything into or for one such combination. Then only we can say it, since it is a 4 to the power of 20 or say 2 to the power of 40 or this much of a number of combinations, you are unable to do that. But even that is also very difficult because of the cross coupling error between the photons. They will definitely try to influence each other's performance or each other's state or information being held. Okay, if they are placed in a very neighboring position to each other. So that is a real problem. And quantum memories cannot store quantum states for a long time due to decoherence. Again, the same thing. All that thing, one is in a 135, one is in a say plus 45, one is in a horizontal, one is in vertical. So exactly they have to hold all the things together if they want to compute some of the function. But quantum memory cannot store quantum states for a long time, and the answer is decoherence, because every such photon will also with course of time decoher. Got it? So, and it's also very costly to implement. Does all the applications of require quantum memories? No, no, not nothing like that. Quantum memory or quantum money, what you were asking? Say quantum money is just a theoretical concept. It is thought of to be one of the applications for memory. Okay. So it is thought of to be one of the applications for this. Definitely, it will not be the case, because every time for each of the combinations, storing it in the database and storing it in form of a memory, that all such combinations should imply to one particular specific information, depending on all the phases, all of their values, what is the polarization angle, all those combinations. So that is very difficult, because every time a lot of memory is going to be wasted for that. And you cannot also hold that much of information for a long time because of the factor that it will decoher. Okay, and it's also very costly to implement. That is $1 million per bill. So now the remaining thing that I have is, just a minute, let me check. So no cloning, intrusion detection, then followed by these things. Okay. So let me have a very small break of, say, maximum 5 minutes, then we will come back and we continue with that. Meanwhile, I guess we were supposed to discuss about the exam, but which we are not today. We will be discussing because few are left with attending the exam. Just one thing, which is very generic one, I guess. So if nothing wrong is there from your end, that is your calculation and all the options are correct, then we will be getting the marks for that. I guess that will be manually also, if not through some automated screening, that will be taken care of. Definitely. So if anything is wrong, like maybe same options for more than one, like same option is given for more than one, like ABCD. So this kind of thing, or somewhere maybe some typo is there. So all these things will definitely be taken care of. That is for sure. I don't know when I'll be discussing, maybe on 22nd or some, whenever the others, the host, they will mention on that class, we will see that okay, if that is logically, your solution should be correct. But please focus on that, whether your logic is correct or not while solution, or while providing, or while giving the solution, or while answering the question. Yes, so there can be some typo. So I guess a lot of these kind of things are happening. So don't really focus on that one. Okay. And theory concept, for some theory questions, just one thing, for some theory questions, I'm not telling that what theory I'm referring to. I hope those who are having that doubt, they will be understanding it. Please focus on the, instead of the direct definition, just try to analyze the options given to you. So every answer is actually hidden in the like question being asked, and all the options give like 4 options given. So it is within that one only. It is your task to cancel it out, that which is correct and which is not correct. Please focus a bit more. Some of the definitions can have an alternative representations as well. So please focus on these two things. Now, it is already, I guess we will start with this thing, the BB84. Yeah. So whatever is the time now, we will start exactly after 5 minutes. So 3:16, we will start. from 321. Okay. Let's start again. Let us start again. So, so this is the BB84 protocol, which is named by two scientists who discovered this protocol, known as Bennett and Brassard, in the year 1984. And also, this protocol was accepted by IEEE and all this after a lot many years. So that was very challenging because it was very theoretical one. So it took a lot of time to be actually finally coming into limelight and all those things. But it is the thought of to be the fundamental protocol for quantum key distribution. Okay. So whenever there is a niche technology, the challenges and everything in terms of R&D, in terms of upscaling and all these things are very, very much of a difficult ones to justify. So it uses a set of 4 polarizers and 2 bases. I discussed just now that bases are or bases can be either a vertical horizontal basis, okay, which is kind of a plus, or a diagonal basis, which is kind of a minus together, where like plus 45 and minus 45 that is being encoded. We also call the horizontal vertical basis as H/V and the diagonal basis as plus slash minus. Okay, because plus and minus has its respective meaning to encode 0 and 1 respectively. Similarly, say horizontal is get 0 and vertical is get 1. Similarly, the zeros and ones are being encoded into these two bases, vertical, horizontal, and diagonal. Okay, now the hexagon that you can see is kind of a filter that you have seen, like that you can see, and what kind of a like photon beam it is allowing to pass, that is shown with the blue color. So depending on its filter, it will allow the beam to be transferred to the other half. Okay, so this is a basic structure of it. So if it is, say, for example, a vertical beam is being passed and the filter that only allows some horizontal beam, so nothing will go. So it will ultimately encode a 0. So nothing will pass through. Okay. Now, similarly, say, for example, if it is a horizontal or a vertical horizontal one, and you try to send a 0, accordingly, some component of that will be passed through. Okay. Now, not the entire one. So in the uh, not correlated basis, it will be some fraction of the information that will be transferred through in terms of the beam, photon beam, but not the entire beam that will be transferred. Okay. So Alice and Bob, both of them will be having 2 pairs of bases. Example is Alice will toss a coin. Now, if she gets a head, or okay, thing is that first initially to start with, Alice will be tossing a coin and Bob will also toss a coin. Now, if Alice gets a say head, say for example, so head determines that she will encode the qubits in the horizontal vertical basis. It is just a convention. If you want, you can also choose a different convention. That for head, we will be choosing the plus minus basis, and for tail, we will be choosing the horizontal vertical basis. But whatever you will choose, that has to be uniform throughout your computation. Okay, and if she gets a tail, she will be encoding qubits in a plus minus or a diagonal basis. Now you can see the picture, horizontal vertical basis. The first one, the row 1, column 1 is horizontal axis. Row 2, column 1 is a vertical one. And similarly, the row 1, column 2, it is a 135 degree. And the last one is plus 45 degree. Okay. Similarly, so how it will be started is, so Alice will toss a coin and generate a random sequences of zeros and ones. Now, if head, maybe I'm using the convention that she will be using a horizontal vertical basis. Otherwise, she will be using, for tail, she will be using a plus minus basis. So each bit in that way, that will be encoded into a 0 or a 1. Okay. Now, Bob receives each bit but does not know how to decode it. Now, Bob, on receiving the bits from Alice, So Alice initially has some random string. Now she will be 0 1 0 0 0 0 1 0, something like that. Now Alice will be using some toss the coin. So on tossing the coin, she can get certain outcome which can be what? Either head or tail. Now depending on that, maybe the outcome of the coin, say for head, Alice is choosing the horizontal vertical basis, and for tail, she is choosing the plus minus basis. Now, depending on the values of zeros and ones, some of the bits will be passed through, some of the bits will be actually blocked. Similarly, that is some of the thing through the basis, it will be encoded, some of the bits of the bit stream. So, and they will be encoded in form of a 0 and 1. If it is the same base, then it will come through. If it is not, then it will be a different one outcome. Now, Bob, on receiving each of the bit, does not know that how to decode it. So, Bob, at his end, he will also toss another coin. Okay. Now, on tossing the coin, Bob can also have a different kind of a basis, right? Because the way Alice and Bob, both of them will toss a coin is completely, or say, at least there is no guarantee that the toss outcomes will be same. So, Bob will be tossing the coin in his own way. And on tossing the coin, similarly, Bob will also try to encode it. Okay. Now, whatever finally, after all those kind of encoding by Bob from the bit stream of finally how Alice is actually using the encoding string to be sent to Bob, and Bob on receiving the encoded string applies his own basis and perform that how many bits he can retrieve finally. If there is a chance that if Alice's chosen basis and Bob's chosen basis are same, then only some of the outcome Alice and Bob will be having the same. And if, say, the basis chosen, they differ. Just like the second case, say Alice chosen the basis or based on the outcome, it is tail, and for Bob, his outcome is head. So definitely that means some different basis will be chosen by both of them. So if this kind of scenario where there is a mismatch, there can be basically fundamentally, that is, the bits will not be passing through, or that will not be actually received by Bob. So we call it that in this particular scenario, there is a 50% probability that something probabilistically that 50% will be received by Bob maybe, and 50% will not be received by Bob because of a difference in basis. Now, where 50% is a definite hit, remember. Now, remaining 50% for these cases also, maybe, as just I have mentioned, maybe if I have, say, a vertical or a horizontal basis chosen by Alice chosen a horizontal one, and Bob may be chosen a 45 degree. So 45 degree and 0, they will be somewhere being plotted. So they will also have some value. So out of the 50% cases where there is initially a mismatch, probabilistically we can say even out of the 50% cases, half of those cases, that is the 25% more cases, there will be a chances of having the same output. Okay. So just like this, you can see the same thing is represented over here as well. So like all these things, this thing 1 0 0 1 1 1 0 0 initially were showing some sort of mismatch. Just see the second, fourth, fifth, and sixth one. Rest of them were a match. Initially, from the initial level, it's a match. So 50% case match, remaining 50 mismatch. Out of the remaining 50, ultimately, in what way it can happen? Maybe because probability is always like uniform. So we can see, or we can like understand it in this way that maybe for the horizontal and the 0, or horizontal and the plus, or say vertical and the minus, or horizontal and the minus and vertical and the plus, there are probability to have certain outcome. So out of the mismatched 50%, there is another 50% sub cases where there is a probabilistically matched scenarios to be taking place. those 25%, class your initial 50% comprises of 75% of the cases probabilist, where it also include the probabilistically matched one. So assuming the theory, just I'm reading through it. So assuming large number of bits being sent to Alice, and Alice is using kind of a random experiment of tossing a coin. That is, half of the time Alice uses horizontal vertical, half of the time she uses a plus minus basis. Assuming also that there is no eavesdropper here. So initially in this picture, whatever we have assumed is only between Alice and Bob. So Alice will be choosing a coin. Based on that, she will be choosing some basis, where initially she will be having some random stream of zeros and ones. Now, based on that, like based on the string that initially she had and the chosen basis of her, she will be encoding a bit string into another bit string. That bit string, whenever sent to Bob, Bob on receiving that, again will toss a coin at his end. Now, based on that, again, he will be choosing a basis. Now, if both the bases of Alice and Bob are matched, that is 50% of the cases of match, and for remaining 50% of the cases there are chances of mismatch, definitely, but still there is a 50% probabilistic options to have a match over the 50% mismatched cases as well. Okay, so for that we will be getting that in another 50% cases, just consider the point number 4, in another 50% of the cases where Bob's basis and Alice's basis mismatch, probabilistically out of those 50%, again for 50% cases, both of them will agree. So thus for 75% of the cases, there will be a probabilistic match. Okay. But here we are only getting this much of a result where there is no eavesdropper or Eve in the scenario between Alice and Bob. Now the agreement between bits sent by Alice and bits received by Bob is as much as 75%. Before generalizing, now just after that, we will also try to at least visualize that what will happen in case of a presence of Eve. Okay, so though the second the third last point is, though Alice and Bob will agree 75% of the time, only for 50% of the time they have used the same basis. And Alice uses a classical channel to announce now. So Bob discards those which disagree. Now what Alice will now say is, okay, I have for this, okay, I'm announcing my, say, 4th bit, 13th bit, 20th bit, and 22nd bit. These are the some bits that I am announcing in public. Bob, based on these bits condition, like configurations of these bit status, will decide if all of them are agreeing. Then definitely there is no error. If that is not agreed, then Bob will assume that there is some error. So accordingly, they will either discard that communication and again start with a fresh bit stream and again choosing the basis and all those things. Otherwise, if it is all okay, they will be going further with making up the key. Okay, this is not the key. First of all, that information that is being passed or say put in public by Alice is some sort of checking. For checking, I am telling. Okay, just like a game theory that that you have to assume who I am. Say, so I'm telling that, okay, so I generally prefer rice over roti. I generally prefer the color red over green. Now you similarly, based on some choices, you have if some of the characteristic features is given to you, you have to analyze if I am the person about whom these kind of things are being referred to or not. Are you getting it? So this is some sort of public information which is known to all, that is being sent now to Alice, sent now to Bob from Alice's end. And if Bob discards, then it will be ultimately the entire communication will be discarded. But this is not the challenge. The main challenge here is, what if Eve is also present here? So also if you see the last part, that after bit transmission, Alice will announce her chosen basis in sequence this in public, not the bits that she sent. So now she will be announcing the chosen basis as well as a few parts of the output, which has no dependency, or from that information, definitely you cannot regenerate or anywhere, anyhow generate the entire one. There is no correlation or no such mapping. And Bob removes all those bits where Alice's basis and his chosen basis do not agree. Okay. And to maintain the uniformity, Bob will agree upon only for those 50% of the time where both bases are same. And for remaining 50% of the time, he is simply disregarding the probabilistically correct outcomes. He is simply cancelling it out. He is not choosing it, though it is probabilistically correct. So ultimately, though, we have an option to get a 75% of the match between Alice and Bob, but ultimately, for the practical realization, Bob will ultimately take into consideration the 50% cases. Now, similarly, here, if presence is not given, say, for example, now, I have another one. Say Eve also, where if should be present. If for quantum key distribution, it should be since I am calling that QKD is free from man in the middle attack. So definitely assuming that man in the middle attack holds true for QKD, that means Eve should be sitting somewhere between Alice and Bob. If is the third party, so Alice, then followed by Eve, followed by Bob. Now, whatever you have done for Alice and Bob, we will again try to redo the same things by Eve as well in the middle layer. So once Alice will have a random bit strings 0, 1, 0, 0, 1, something like that. Alice will be using a say tossing a coin, and through that coin outcome, she will be choosing some basis. Based on the basis, she will be encoding her string at her end. Nothing is public. Now, if what will do, she will do is, Eve will also try to impersonate to Alice in the way that Eve will also toss a coin, just like Bob. So Bob is also tossing a coin, who is the intended receiver, and Eve, being an intruder, also is tossing a coin. Now, based on the tossed outcome, Eve is encoding something, and that result finally is being passed to Bob. Now, if you check it, if you now notice about one factor as well, that say for example, wherever, so when or where are those cases where Bob will receive the same information as it is sent by Alice. So Alice is the intended sender, Bob is the intended receiver, but when I am supposed to get that one? Only when Eve's chosen basis and Alice's chosen basis and Bob's chosen basis, all of them are same. Right? Otherwise, since it is photon, so it will not pass through, so we are not going to get any outcome. So if it is a passing through the beam, this kind of thing has taken place, then definitely that means that my filter has to be the same. Okay. Now, once this happens again, say for example for Alice and Bob, and in between Alice and Bob, Eve, say in how many cases it can be like all of them are same thing, all of them are same basis. It will be like in case of a 25% of the cases. So it's half into half, kind of that. Right? So it's a 25% of the cases where we can assume that it will be same. Now, also you have to remember this thing that what will happen simply. Say, for example, I have something, I am Bob, I have some information received from Alice with certain probability, where I am assuming that Eve is also present. And what is the probability? 25%. So 25% of the cases is where somewhere I like that is guaranteed at each of the iteration. 25% case is guaranteed at each of the iteration, even if Eve is present between Alice and Bob. Now, on that note, can I claim one more thing here? That what if instead of sending only n bits and losing out all those bits, what if I have to successfully receive n bits as output, Why can't I send 4 into n number of bits as my input? We can definitely do that. Then only it will be 25% of that, which is again n, which is my kind of a requirement that I have. Okay, that is why we call in BB84, we generally should always go for a 4n plus some x or say delta. Delta is the additional bit, some of the additional bits just. So at least 4n number of bits should definitely be there along with some 1 or 2 or 3 more number of bits. Okay, so if someone asks you that for quantum key distribution in presence of Eve, how many, in order to send n bits, how many bits you actually need to be sent, or how many bits should be the size of the data word, something like that. So your answer will be, options will be say 4n plus delta, option B 2n plus minus delta, option 3 say n by 2 plus delta, and option 4 something, anything like that, say n minus into delta, anything. So it will be 4n plus delta. Why? Because of the 25% of the cases. And why this is happening? Because probabilistically at every decision point, it will be exactly half of half. So that's why initially it was 100%, it was half. Then it again got reduced to another half. No cloning theorem is, which is a positively culprit between these things, which is why the QKD is thought of to be very, very much secure. So a copying device can only clone orthogonal states. I told it that either two states will be like same, or they should be somewhere in an orthogonal relationship with each other, if you remember. Okay, so since an arbitrary superposition of states is not orthogonal, cloning of quantum states is not possible. And second point is, this is fine only under the assumption that there is no Eve intervening between Alice and Bob through the public channel. And now that if Eve has a possibility to tap into what Alice sends and keep that and make an identical copy, this is also prohibited by no cloning theorem, because Eve cannot under any condition can able to make an arbitrary or say identical copy. An intrusion detection system in quantum world, just like the man in the middle attack that was there in the Diffie-Hellman or Diffie-Hellman key exchange protocol, because somewhere in between, say intended sender and receiver might impersonate as to be a intended receiver for the sender, or intended sender for the second receiver. This can happen, but so presence of Eve in classical communication cannot be detected with certainty. Okay. So in quantum mechanics, the process of measurement itself disturbs the state for fundamental reasons. Similarly, the no cloning theorem is the phenomena, and how this is helping us is through the intrusion detection. Because since it cannot be cloned, so any way of like touching the system or say photon will result in either a change in the state of the photon, or it will be somewhere like decohered, some sort of error will take place if we try to measure the system. For instance, because of the uncertainty principle, if Eve measures one of a pair of non-commuting observables, the other variable is randomized. Okay? Why this is happening? Because of the non-contextuality. Nothing is contextual. It's very uncertain. And position and momentum, they are also very uncertain. So nothing you can actually predict beforehand because it is purely random. Now, just before these things, also of one point I want to discuss about this. How much is the time left? Can anyone just let me know what
Uh,
is the current time?
10 minutes remaining, ma'am.
Okay, okay. So just this will not take much time. These are just some of the use cases of quantum cryptography and a few of the future research areas. I have very less amount of time. So quantum random number generator, I was discussing, or maybe a few words I also have shared in the last class, because quantum random number generator is thought of to be another very promising area, just like UKT for quantum cryptography. Just remember here, the fundamental idea is there are several types of quantum random number generator. Mostly you can think it of some sort of optical quantum random number generator, where some optical or photon you are using in order to create the randomness or entropy. But just a few phenomena of it. For a hardware based random number generators, you just need to verify the hardware property of the random number generator as well, for which you have to go for the lab test and all. Another kind of a randomness testing that you can do is you have to rely on the statistical testing. Okay, so those are statistical tests of randomness, and first one is the hardware kind of a testing for pure randomness. So since we have both the type of a random number generator, for example, say ID Quantic, they have their own random number generator. So they are offering different with a different, say, bits per second. That much of a capacity of a random number generator they are offering. If you just check it, depending on your application or how secure you want to make your applications to be, or how fast you want your random number generator to generate the random bits, based on that you will be choosing the vendor for your particular specific applications. Just my point for you is, just remember that the statistical tests that we use are mostly based on the NIST statistical tests, which is 822A, B, C. All these tests are used. Also, the die-hard test or die-hard test, they are also another kind of a statistical test, where we actually use that how many frequency are there, or say what is the cumulative frequency, what is the kind of entropy with respect to different blocks. So block wise, likewise, there are 15 statistical tests for NIST, but all of them are statistical one, not the physical level. Got it? And second point is, always remember that for a random number generator to work on or to check into, you have to really consider a very big number of bits. So just to give you the essence on how big it should be, for statistical testing, it is generally at least your file size of random bits that you should fit into the statistical test suite. It should be a 10 million number of bits for one such operations to be taking place. Otherwise, it will not able to pass through, or it will not allow you to give it as an input. So at least 10 million. And why that is the case? Say, for example, I have given you a 8-bit string, say 00000011. If I ask you, is it random? Or second one, say 00110011. Is it random? Third one, 0011, 00001111. And the fourth one, 01010101. Quickly, just a quick checking. Just tell me which is more random here. Can you tell me? First option was 8-bit string. Option A, you have to just mark whether it's option A, B, C, or D. Option A is 000000, 6 zeros followed by 2 1. Option B is 00110011. Option 3 is 4 zeros, that is 0000 followed by 1111. And option D is 01010101. Can any one of you tell that which of these options, 4 options, is more kind of a random? Can any one of you answer it? B, which is 0011. Okay. All of you are wrong. All of you are wrong, because none of them are more, because all of them are equiprobable. At every instance, I can have any output. And my first outcome, that is say 0, is completely independent of the second one. And also for such a small number of bits, only for 8-bit string, I can compare nothing. Okay? Because it can be that like that okay, if I consider, say, the frequency testing, then frequency testing on the 8 bits will say, tell me that the option D seems to be perfectly random, more like a perfectly random solution. But it is not the case, because in that much of a like a size, and small, like minutely small size, to check randomness, we cannot see anything natural, and it has to be perfectly natural, right? So that frequency, after which it should again repeat, that has to be really after a significant amount of time. And also uniformity is another challenge or aspect here for a random number generator. So 0101 seems to be more uniform, so you can call it more uniform, but you cannot call it more random, because all of them are equally or equiprobable. So all of them are, none of them of random. Either you can say that, or you do not know that whether some of them are not non-random. You can claim that I cannot claim that they will really be non-random if I again keep on generating them for a infinitely large number of such bits. If I keep on adding them, I do not know whether that will be random or non-random or not. I cannot predict that. Okay, that's that much of an introduction, and just sorry for this. I have not added any slide, but I hope if you just follow the like recording and all, you will be having the idea for the Q1 and G. Uniformity is definitely different from random. Definitely. Random means it can be, if it is like all zeros, 0, 0, 0, 0, 1, 1, 1, 1, and I have a combination or a set of 0, 1, then all 8 zeros are also random, but it is not uniform. Because uniformity means your number of zeros and ones should be somewhere at least related. If not exactly equal, they should be exactly equal or almost equal. So it's a non-uniform but random. But for statistical tests, uniformity is another very important measure for randomness. So if you have to check randomness as well as uniformity, you really need to feed a very long number of zeros and ones. So in that 10 to the 10 million bits, if it is generated from a purely random source, definitely will be having some essence of uniformity as well as randomness, but they are different. Okay. There are several QKT algorithms like E-card protocol and the BB84. Just like BB84, there is another one for BB91 protocol. So these protocols are there. But these are two technologies. This is not exactly algorithm, but these are technologies. No, not really. Not really any encryption decryption algorithm is there, because here we are only focusing on the key distribution. Key distribution algorithm is not same as a key encryption algorithm. Definitely. But the thing is that data encryption algorithm is when it is unsafe because of the key itself. So the thing is that if your key, it is a random key, and if you are able to distribute it randomly, like say quantumly through a quantum channel, then data is nothing. Data means, I mean, data you can never get it. Data breaking is only possible through key. Key is the fundamental essence. Just if you remember AES 120 and all those things, where we for sure for Grover, or in all these cases, we are only considering the breaking the key. Data, we are not all like touching the data. Shor is claiming that, okay, I can break the key, the public key, private key, the RSA algorithm. RSA algorithm means ultimately the key, where the large number is divided into two keys, the like public key and the private key. For example, if it is the case, then how to get that? Once we have the key, we have the rest of the cases. Similarly, for Grover, the key space initially for ASA 256, it was 2 to the power 256. Grover is claiming that I can make the key space size reduced to 2 to the power 128, which is a quadratic reduction. So it is again another advantage. So quantum also is working as a solution for these areas particularly. It has identified that where exactly some error can happen. Okay, so here a quantum channel will be there where a quantum key will be distributed using a BB84 protocol or some other advanced QKD protocols. Definitely BB84 is not very much of a reliable one. There are other advanced ones as well, but this is very fundamental. E-card, BB91, and also maybe some application specific ones, you can also tune it. Just like you can tune your Grover and QAA for some applications, similarly, you can do all these things. But this is an algorithm for the key distribution, not for the encryption. But for PQC, in post-quantum cryptography, we have an encryption-decryption algorithm, which is called the Crystal-Kuiper algorithm, which is a key encapsulation mechanism. Okay. Okay. Just 5 minutes. You can also like go through these things. So quantum key distribution for banking transactions. Just go through that. So once you have a problem statement where the encryption algorithm for online transactions, they actually they are vulnerable because of the RSA and AES, vulnerable to quantum attacks. The classical pitfalls is they rely on the mathematical complexity, which quantum algorithms can break. So the data theft and financial fraud risks will increase. Quantum solution is a QKD enables unbreakable encryption, or say perfectly information theoretic security by leveraging the laws of quantum mechanics, and it is providing quantum advantage because the secure communication channels resistant to quantum decryption. So that is a quantum advantage, and instant detection of eavesdropping. So if any interception disturbs the quantum state, so immediately that will be discarded. And also in presence of if, just please remember, because there is 25% of the cases that there will be a properly whatever sent by Alice will be, even in presence of if, will be retrieved or received by Bob. So that 25% we are considering. So for one, it is 25%. If we have to send n bits, n such bits, it will be 4n. Plus additional few of the parity bits we also check, add for further checking. So it's a 4n plus delta number of qubits. 4n plus delta number of, sorry, not qubits, 4n plus delta number of bits. Okay. Business impact is banks adopting QKT can protect high value financial transaction, regulatory compliances and all, trust and brand reputation. Likewise, just go through the solutions. You can go through them. I guess 6 are there. Yeah. Also for them, the future research area, few of, I guess 2 or 3 of you asked about it. I guess you can go through these things. Just like 1 or 2 words will be for QML. It is a hybrid one that is currently you can think it of. Few use cases will be getting from the slide itself. It is very in a very early stage. So current challenges, keep in mind the current challenges and accordingly choose a perfect problem statement or find what solution you can provide with respect to the current state of the art. So it's a quantum data encoding that is very difficult. Noisy quantum system. So again, a challenge, hybrid ML model. So combining or finding the interface between the classical ML and quantum ML is a challenge, and QML is still in the early stages. So though exponentially we can see an acceleration of model training through the HHL or Harrow-Hassidim-Lloyd algorithm for quantum machine learning, there are a lot of challenges. So if you can work in any of these challenges, that will be a breakthrough. Then like a quantum feature encoding, quantum neural network, quantum generative adversarial network, and variational models. So all these things are there. For few use cases I just mentioned over here. Optimization is where actually the research topic is around the QAOA or quantum approximate optimization algorithm for any various optimization tasks. Okay, but again, noise sensitivity, scalability is the biggest challenge. Benchmarking, how to actually you can identify or how you can specify the metrics in order to state that which is better, classical solver or a quantum solver. That is also very difficult because none of them are really in the same page. It's just like comparing an apple and an orange. So you have to find a medium between both of them where both of them will agree in terms of something. So optimization is another very promising area. Hybrid one, portfolio optimization, quantum assisted traffic flow optimization, all these things are there. Quantum cryptography may like QRNG is the biggest one. Then QKD networks, they are not really scalable. So that is why quantum repeaters, you have to put it because in quantum channel also, theoretically it is very secure. But again, some attenuation or noise level can take place. So signal attenuation can also happen in between the sender and receiver. So at multiple points, just like a checkpoint, you should be adding some quantum repeaters. PQC, so ongoing one. Anytime you can select this one. But honestly, PQC is not really that easy or easy cup of cake, to be very frank. Though it's a classical one, but the mathematics itself and all those things are very difficult and they are really not something very easily implementable. So these are very difficult algorithms. I just want to mention it over here. Quantum hacking risks, that also is there. And so developing a scalable quantum safe encryption is a top priority for global cybersecurity. So quantum resistant blockchain, satellite based quantum cryptography, zero trust security with quantum authentication, all these things are there. Okay. And sensing, I do not know much of the sensing thing. Maybe tomorrow onwards we'll be having a better idea of it. But yes, definitely quantum sensors are there to detect the gravitational waves. And then just like your classical sensors, it's a quantum sensors where the particle which is used as a sensor, it is working in the quantumly or that much of a level, quantum say nanoscopic level. So to monitor the brain activity to improve the GPS precision beyond your classical limits, applications span the healthcare, defense, oil exploration, and space technology, space tech. Quantum enhanced imaging can revolutionize the medical diagnostic and the climate science. Okay, so making it compact and portable is a challenge. How to reduce noise and decoherence in real-world applications is another challenge. Commercial scalability, definitely. Mass production for industries is a challenge. All of this will be was a challenge for semiconductor also. Maybe 50, 60 years back, but right now we can see that how revolutions has taken place. Similarly, maybe here also, we need some more time for it, nothing else. These are some of the key research areas. You can check it out by yourself. And here is where I guess I can stop. Okay. Happy colorful Holi of you. That is the end.
Thank you so much, ma'am. Thank you for the wonderful series of lectures that you have taken. मैं बंद कर एक मिनट वेबएक्स इसमें भी है जिसमें Yeah, thank you so much, ma'am, for your time and so much of information that you have passed on. And I hope the participants have learned very much. We will have a short meeting with you for the questions. They have some doubts, so maybe not today, but after the second exam is also over, we'll have, because communication also you can come and cover maybe 15-20 minutes. So and hopefully we'll look forward to hearing from you again in quantum QT02, the quantum foundations, quantum technology foundations, or foundations for quantum technologies, FQT, the next course that is there. So as ma'am will be taking few lectures there also. Thank you so much for your extensive time, sending the slides and also preparing and updating the slides. I have attended the 2021 series where we have coordinated as MNIT Jaipur. And there has been a lot of depth that has been increased, and I hope the participants have received the best. So and also, of course, there is less time for a lot of what do you say interaction, because the content was so much that we could not have time to have question and answers in that particular way. But then it has been a great time of learning for everyone, and hopefully maybe we'll have a open house kind of thing where people